In this section, we will discuss measures of relative standing. A measure of relative standing is a number showing the location of data values relative to other values within the data set. In this section, we are introduced to measures of relative standing, which are numbers showing the location of data values relative to other values within the same data set. The most important concept in this section is the z-score. We also will discuss percentiles and quartiles, which are common statistics, as well as another statistical graph called a box plot. Simply put, a z-score, also called a standard score, gives you an idea of how far from the mean a data point is, but more technically, it's a measure of how many standard deviations below or above the population mean a raw score is. The z-score is calculated by one of the following equations. For a sample, the z-score is the observation minus the sample mean divided by the sample standard deviation. For the population, the z-score is the observation minus the population mean divided by the population standard deviation. When you round z-scores, you'll want to round them to 2 decimal places, such as 2.31. The round-off rule for the z-score is motivated by the format of the standard table in which z-scores are expressed with 2 decimal places, as in the table A-2 in the appendix of this textbook. Let's review some important properties of a z-score. A z-score is the number of standard deviations that a given value of x is above a mean or below a mean. The z-scores are expressed as numbers with no unit of measurement. A data value is significantly low if its z-score is less than or equal to -2. That is to say, a z-score of -2 tells us the value of x is 2 standard deviations below the mean. A data value is significantly high if its z-score is greater than or equal to +2. In other words, a z-score of +2 tells us the value of x is 2 standard deviations above the mean. And finally, if an individual data value is less than the mean, its corresponding z-score will be negative. Let's use z-scores to compare the weight of a newborn to the body temperature of an adult. Which of the following two data values is more extreme relative to the data set from which it came? Our first data value is the weight of a newborn from a sample of 400 newborns. This newborn weighs 4,000 grams. The mean weight of the sample of newborns is 3,152 grams. And the sample standard deviation of our sample of newborns is 693.4 grams. Our second data value is the body temperature of an adult from a sample of 106 adults. This adult has a body temperature of 99 degrees. The mean temperature of our sample of adults is 98.2 degrees Fahrenheit, and the sample standard deviation is 0.62 degrees Fahrenheit. We can standardize both the weight of the newborn and the body temperature of the adult by converting each to a z-score. This is done by using the z-score for a sample. So for our newborn with a weight of 4,000 grams, our equation will be 4,000 grams minus 3,152 grams over 693.4 grams. That gives us a z-score for our newborn of 1.22. For the body temperature for our adult, our z-score will be 99 degrees minus 98.2 degrees divided by 0.62 degrees. That gives us a z-score of 1.29. The z-scores show that at birth a weight of 4,000 grams is 1.22 standard deviations above the mean birth weight. while a temperature of 99 degrees is 1.29 standard deviations above the mean adult body temperature. Because the adult body temperature is farther away from its mean, it's more of an extreme value than the birth weight of the newborn. The z-score tells you how many standard deviations an observation is from the mean of a data set. Previously, we used the range rule of thumb to determine if a value is significantly low or significantly high if that value is at least 2 standard deviations away from the mean. It follows that significantly low values will have a z-score that is less than or equal to -2, and a significantly high value will have a z-score that is greater than or equal to +2. Using this criterion for both the newborn weight and the adult body temperature, we know that neither value is significantly higher than the mean because both z-scores are between -2 and +2. In this example, we want to find out if a platelet count of 75 is considered to be significantly low. Let's say we have a subject whose platelet count is 75, and it happens to be the lowest platelet count in our data set. We want to know if this value of 75 is significantly low. Assume the platelet counts have a mean of 239.4 and a standard deviation of 64.2. We can convert our subject's platelet count to a z-score. So we plug in everything we have into our formula for a z-score, and we get 75 minus 239.4 divided by 64.2. This gives us a negative z-score of -2.56. The platelet count of 75 converts to the z-score of -2.56. That is to say, this platelet count is 2.56 standard deviations below the mean platelet count. So we would say in this case that the platelet count of 75 is significantly low. A z-score is a measure of position, but percentiles are measures of location, and we denote percentiles with P1, P2, and so on all the way through P99. This divides a data set into 100 groups with about 1% of the values in each group. Another way to describe percentiles is that a percentile is a number where certain percentages of scores fall below that number. Percentiles are commonly used to report scores in tests like the SAT, the GRE, or the LSAT. For example, the 70th percentile on the 2013 GRE was 156. That means if you scored 156 on that exam, your score was better than 70% of all of the other test takers. The process of finding the percentile that corresponds to a particular data value x is given by the following. The percentile of x equals to the number of values less than x divided by the total number of values multiplied by 100. With a percentile, you will want to round to the nearest whole number. The table presented here displays the 50 Verizon data speeds listed in Dataset 32 in Appendix B of this textbook. For this example, we have arranged the cell phone data speeds in increasing order. So let's find the percentile for the data speed of 11.8 megabits per second. From the sorted list of airport data speeds in the table, we see that there are 20 data speeds that are less than 11.8 megabits per second. So we can say that a percentile of 11.8 is the number of values that are less than 11.8 divided by the total number of values multiplied by 100. So that gives us 20 over 50 multiplied by 100 gives us 40. So we would say that a data speed of 11.8 megabits per second is in the 40th percentile of this data set. This can be interpreted loosely as the data speed of 11.8 megabits per second separates the lowest 40% of the values from the highest 60% of the values. And we would write this as P40 equals to 11.8 megabits per second. Let's review some notation that we will use with percentiles. N is the total number of values in our data set. K is the percentile being used. For example, the 25th percentile, K will equal to 25. L is the locator that gives the position of a value. For example, the 12th value in a sorted list will be L equals to 12. And finally, P subscript K is the kth percentile. For example, P subscript 25 is the 25th percentile. These are the steps involved in finding a percentile. The first thing you do is you sort your data from smallest value to largest value. Next, you compute your locator using the formula L equals to K divided by 100 multiplied by N, where K is the percentile of interest and N is the total number of observations in the data set. If L is a whole number, then the kth percentile is midway between that Lth value and the next value in the sorted data set. To find the kth percentile, simply add the Lth value to the next value and divide by 2. If L is not a whole number, round the L value up to the next larger whole number, and the kth percentile is the up-rounded Lth value, counting from the smallest value in the data set. Let's use our table of data speeds to find the 40th percentile. We'll denote this as P subscript 40. We can find the 40th percentile by computing our locator L. Recall that K is the percentile of interest. So in this case, K equals to 40. And N is the total number of values in our data set. So in this case, N equals to 50. Let's plug those into our L formula and calculate L. So we get 40 over 100 multiplied by 50 gives us a value of 20 for L. The locator L gives us the position, but since L is a whole number, according to our steps in finding a percentile, we will need to find the middle value between the 20th value and the 21st value. The 20th value in our table is 11.6, and the 21st value in our table is 11.8. So we add 11.8 to 11.6 and then divide by 2. So 11.7 megabits per second is the 40th percentile of our data set. Quartiles are values that divide our data into quarters. More formally, we say that quartiles are measures of location denoted with Q1, Q2, and Q3, which divide our data into 4 groups, with about 25% of the values falling into each group. More specifically, quartiles can be described as the first quartile, Q1, is the same value as P25. It separates the bottom 25 of the sorted data values from the top 75. Quartile 2, or the second quartile, is the same as P50, and it is also the same as the median. It separates the bottom 50% of the sorted values from the top 50% of the sorted values. The third quartile, or Q3, is the same as P75. It separates the bottom 75% of the sorted values from the top 25%. Finding the quartiles can be accomplished with the same procedure for finding percentiles. A note of caution: there is not universal agreement for a procedure for finding percentiles, and so there is no universal agreement on a single procedure for calculating quartiles. And different technologies will often yield different results, so you just need to be aware of that. In previous sections, we described several statistics, including the mean, median, mode, range, and standard deviation. Here we'll look at other statistics that are defined using quartiles and percentiles. The first is the interquartile range, or IQR, and it's simply the difference between the third quartile and the first quartile. The semi-interquartile range is the third quartile minus the first quartile divided by 2, and the mid-quartile range is the third quartile plus the first quartile divided by 2. The 1090 quartile range is simply the 90th quartile minus the 10th quartile. The 5-number summary gives you a rough idea about what your data set looks like. The 5-number summary is useful to find other statistics such as the interquartile range. For a set of data, the 5-number summary consists of these 5 values: the minimum value, the first quartile, the second quartile or the median, the third quartile, and the maximum value. Let's find the 5-number summary of our Verizon Airport data. Because our Verizon Airport data speeds are already sorted in ascending order, it will be easy to find the minimum value and the maximum value. Here we can see that 0.8 is our minimum value for our data set, and 77.8 is our maximum value for our data set. So we now have 2 out of the 5 numbers for our 5-number summary. We'll use our locator equation to find each of the quartiles. First, we'll let L equal to 25 over 100 multiplied by 50. That gives us 12.5. We round that up to 13. So at the 13th position, we'll find our first quartile of 7.9. Next, we let K equal to 50, and so our second locator value will be 50 over 100 times 50. That gives us 25. Because that's a whole number, we'll want to find the midpoint between the 25th value and the 26th value. And here we find the mean between 13.7 and 14.1 because those are our 25th value and our 26th value. So our second quartile is 13.9. And finally, if we want to find our 75th percentile or our third quartile, we'll use our locator value, and we'll let K equal to 75 over 100 multiplied by 50. This gives us 37.5, and we round that up to 38. So at the 38th position, we find that the third quartile is 21.5. So our 5-number summary for our Verizon data speed data set is the minimum value is 0.8 megabits per second. Our first quartile is 7.9 megabits per second. Our second quartile, or our median, is 13.9 megabits per second. Our third quartile is 21.5 megabits per second. And finally, our maximum value is 77.8 megabits per second. We can use the 5-number summary to construct a box plot or a box and whisker diagram. A box plot is a way to show the spread and center of a data set. A box plot is a graph of a data set that consists of a line extending from the minimum value to the maximum value, and a box with the lines drawn at the first quartile and the third quartile, and finally a line drawn through the box to represent our second quartile or our median. The first step in constructing a box plot is to find the 5-number summary of your data set. The second step is to construct a number line that extends from the minimum value to the maximum value. In the third step, you construct a rectangle that extends from the first quartile to the third quartile. And finally, you'll draw a line through the rectangle at the value that is the second quartile or the median. Let's use our 5-number summary and construct a box plot for our Verizon Airport data. Using the 5-number summary for our Verizon data, we can construct our box plot. Recall that we have a minimum value of 0.8, our first quartile is 7.9, our second quartile or our median is 13.9, our third quartile is 21.5, and our maximum value is 77.8. The first step is to draw a line that extends from 0.8 to 77.8. Those are our minimum and maximum values. Then we draw a rectangle across that line that extends from our first quartile to our third quartile. So on our number line, we'll draw a rectangle that goes from 7.9 to 21.5. And finally, we'll draw a line through the rectangle that crosses that number line at 13.9, where our median is. And this is everything you need to do to construct your box plot. Box plots are useful because they show the skewness of a data set. A distribution of data is skewed if it's not symmetrical and extends more to one side than it does the other. In a box plot, if the median is in the middle of the box and the whiskers are about the same on both ends of the box, then that distribution is considered to be symmetric. When the median is closer to the left end of the box and the whiskers are shorter on the lower end of the box, then that distribution is said to be positively skewed or skewed right. When the median is closer to the right end of the box, and if the whiskers are shorter on the upper end of the box, then that distribution is negatively skewed or skewed left. The box plot of the Verizon data show that the data are skewed right because there is a longer tail on the right side. When analyzing data, it's important to identify and consider outliers because outliers can have a powerful effect on the statistics that represent our data set. Recall that an outlier is a value that lies very far away from the vast majority of the other values in your data set. For now, we can construct a modified box plot and consider outliers to be the data values meeting specific criteria based on the quartiles and the interquartile range. The steps for identifying outliers using a modified box plot are as follows. First, we find the quartiles Q1, Q2, and Q3. Second, we find the interquartile range, where the interquartile range equals to the third quartile minus the first quartile. Third, you evaluate 1.5 times the interquartile range. And finally, in a modified box plot, the data value is an outlier if it is above the third quartile by the amount greater than 1.5 times the interquartile range, or below Q1 by an amount greater than 1.5 times the interquartile range. A modified box plot is a regular box plot constructed with these modifications. First, a special symbol such as an asterisk, a point, or an X can be used to identify outliers as defined previously. And second, the solid number line extends only as far as the minimum data value that is not an outlier and the maximum data value that is not an outlier. Using our Verizon dataset, we can create a modified box plot to identify any outliers in our dataset. The first step is to find our quartiles, which we've done previously. So we know that Q1 is 7.9 megabits per second, Q2 is 13.9 megabits per second, and Q3 is 21.5 megabytes per second. Next, we find the interquartile range, and that's simply Q3 minus Q1. So that gives us 21.5 minus 7.9 equals to 13.6 megabits per second. Next, we evaluate the equation 1.5 times the interquartile range. So that is 1.5 times 13.6, and that gives us 20.4. Now, any value that is above the third quartile more than 20.4 megabits per second would be considered an outlier. Also, any value below the first quartile that is more than 20.4 megabits per second below that value would also be considered an outlier. As you can see, the smallest value in our data set is 7.9, and so there are no outliers below the 7.9. However, we have 4 values that are above the third quartile by more than 20.4 megabits per second. And those values are 43, 55.6, 71.3, and 77.8. So we could consider those 4 values to be outliers in our data set. This is the end of Chapter 3. The Chapter 3 module is posted. The videos are on our YouTube channel, and the slides are also posted in the module, and the homework assignment is also posted. Let me know if you have any questions about the material we learned in this chapter.